So here we're going to take a look at ozonolysis. Ozonolysis is a reaction that generally works with alkenes and alkynes. And typically the purpose of this reaction is to cleave the pi bond and break it up into two separate pieces, separate molecules. And in a very basic way, this reaction works by, again, taking an alkene and adding ozone to it. Now, one of the things that makes this reaction kind of easy to monitor at times is ozone is blue. And if you add ozone to your reaction, as long as you have alkene and it's reacting, the blue color from the ozone will go away. Once all of the ozone or all of the alkene has reacted, at that point, the ozone won't react anymore, and it'll stick around, and your reaction will start to turn blue. When that point reaches, and usually it happens pretty quickly, typically at that point you add either zinc and water or dimethyl sulfide. Now there are other things that you can add at this point in the reaction that will give you different types of products, but we're just going to sort of focus on the simple examples here. But the result is that it will cause this double bond to cleave. And you end up with a carbonyl on both carbons of what was the alkene. So this reaction has been known for actually quite a long time. First discovered back in the 1840s. By Schonbein. And while we don't generally cover the mechanism of this one in lecture, I am going to go through it here so that you can get an idea of what how this reaction works. So the mechanism here is one of our first examples of what we would call a cycloaddition. And by cycloaddition, what we mean is that the reaction, the mechanism, happens in a cyclic state, as we'll see here. So the double bond, the alkene, attacks the oxygen, the pi electrons shift over, and then the extra electrons from this oxygen attack back to the alkene. And that forms this intermediate here, known as an ozonide. In the next step, the ozonide breaks apart, and we form what looks like one of the final products. But as you can see, the other one isn't quite there yet. Now, you might think that only that second one is going to react, but it turns out that these two species will actually recombine. And what happens is we form a new 5-membered ring, which is also considered a type of ozonide, but you can see it's got a slightly different arrangement. Now, if we look at dimethyl sulfide as what we add, what happens is that the sulfur, the lone pair, will attack the oxygen, and that will at least initially break open the 5-membered ring. But what we've also accomplished in this step is we've made a leaving group. And so now this lone pair adds in, breaks it open, and we kick out dimethyl sulfoxide as a leaving group. And so you can see we end up with a carbonyl here from the top, carbonyl from the bottom, and then the byproduct, dimethyl sulfoxide. Now, when it comes to applications for things like ozonolysis, we're not going to get into a lot of applications for a reaction like this because primarily the applications for this reaction are synthetic. Ozonolysis can affect a large number of other functional groups, so you have to be very careful with the use of ozonolysis. It will certainly affect other alkynes and may affect other functional groups as well. So we're just going to conclude this video by showing a couple of other examples. And it could be, a very, very simple alkene. Again, the bond that breaks is always the alkene in between the two carbons of that alkene. And each carbon of the alkene ends up as a carbonyl. One place where it can look a little bit more complicated, even though it's the same reaction, is if your starting material is cyclic. So if your starting material is cyclic, even though we're going to cleave that bond, we still will only end up with one compound, and that's because the ring is still connected in another spot. And so we still end up cleaving the carbon-carbon double bond, but we end up with only one molecule because it's still connected on the other side.